I'm a PhD student at Ram Research Institute. Firstly, thanks to the organizers for this opportunity, and given that this is the last talk of the workshop, it's a privilege, and I would aim to end it on a bright note. I'll be talking about the prospects of detection of a monopole global signal using interferometers, and this work has been done under the guidance of Dr. Saurabh Singh. So I'll try to motivate the need for an interferometer when we have single element radiometers doing the job for us. And for that we'll look at the response of the interferometer itself for different sky distribution, including the monopole sky and foregrounds. And we'll see the consequences of having arrays of different elements of interferometers and baselines of different lengths. And how do we combine these baselines to get your data. And I'll be concluding by the powers of what a photon sees and signal by the interferometer and some inferences regarding that. The signal itself, we are focusing on the frequency range from 40 to 200 megahertz, encompassing all of the epoch of reionization and cosmic dawn data. And for us, what matters in the signal is that it's monopole. We don't really worry about the spectral feature of the signal itself. It is just a monopole of 100 millikelvin amplitude across all 40 to 200 megahertz. As Saurabh talked about in his talk before, the global experiments for the global 21 centimeters is focused on single element radiometers. And this makes sense because interferometers, we have different baselines which are sensitive to different spatial modes on the sky, and it is generally thought that interferometers are sensitive to temperature fluctuations in the sky, and it's the radiometers that are sensitive to a non-varying sky signal. And but the challenge, if you ask for these experiments, they would say that yes, there is RFI, there is foregrounds, there is ionosphere doing funny stuff, there is your instrument sensitivity itself, that's a challenge. But the major bottleneck for these experiments is the instrument systematics. And with regard to a radiometer, you would have everything that you need to precisely calibrate. You would have reflections from your additional cable lengths, you would have additive systematics, you would have multiplicative systematics as well. And here I would like to point out that interferometer, when you cross-correlate between two elements, you essentially remove the additive systematics in your system. And this is a big advantage. And that motivates this study, whether we can exploit this advantage of interferometer where you are immune to additive systematics, and whether we can have sensitivity that can detect a monopole signal. So going to the response of the interferometer itself, it is given by this integral over here. There are different versions of this. And this is where you are solving the integral in angular coordinates. Your theta and phi are related to the declination and RA of your sky coordinates. A is your antenna beam, T sky is your sky distribution, and the exponential term has the dependence of baseline and your pointing direction. So to lay the groundwork here, let's consider two element interferometer, a basic dipole interferometer. There can be two geometries possible. You can have two parallel dipoles and an inline dipoles as shown here. And the coordinates are that your y-axis is pointing to the zenith, your antennas are on the XZ plane, and your baseline, which is the separation between your two elements, the vector that is pointing towards the centers of these two, are along the x-axis in both cases. And based on this geometry, you can solve this integral. So LHS is the visibility, it's a complex number. Essentially tells you the response for your T sky. The 4 pi term here is your beam normalization. For an isotropic beam with uniform weights you have 4 pi, but for a different beam you would have different normalizing factor. And essentially if you solve this integral for theta and phi, you get a response something like this for T sky of 100 millikelvin. So note that here, the T sky 100 millikelvin is independent of sky coordinates, which is monopole and global component. It comes out of the integral, and essentially you solve for the rest of the terms. And the real part of your integral response is this in terms of baseline. So this is baselines in wavelength, b by lambda, and there are a few things to note here. At zero baseline, which is essentially a zero baseline interferometer or the one element radiometer case, you get the maximum response of 100 millikelvin. You recover the entirety of your monopole component. And once you have the interferometer with finite baselines, you probe something along the U plane or B by lambda plane, and your response drops by sync function for your T sky. And essentially, this is the reason why radiometers are used for global signals, because it has the maximum sensitivity, and interferometers lose sensitivity as you have longer and longer baselines. So for the three cases there, parallel, inline, and demonstrate an ideal case of isotropic antenna, you can see that the parallel antenna behaves better, whereas the inline component response dies down very quickly with larger baselines. There was another component, which is the complex or the imaginary part, and as can be seen, note that this y-axis is of the order 10 power minus 16. So essentially for a monopole sky, your imaginary or the term is 0 for a monopole sky, because imaginary component essentially captures the phase information of your sky distribution, and for a non-varying signal, you would expect 0 phase, and that's why you have a 0 imaginary part there. So we will fix the isotrope. We'll fix the parallel configuration as the basic interferometer element for us, and we'll work with that. One thing to highlight here is that you see that there is a drop in response. Can we increase this response at higher baselines? And no, this is very low. We are reaching machine precision, so it's 10 power minus 16. So those are just artifacts. So we can increase the response by having arrays of this interferometer, and this parallel configuration, we can have arrays in end-fire mode or the inline array of parallel combinations. And essentially this number, we have n equal to 3 here. There are 3 parallel interferometer elements, and essentially what it does is it increases the gain of your antenna, and your effective antenna beam is multiplied by this array factor square. And if you plug in this to your integral, you would get a response something like this for different n values of the array elements. And as can be seen here, increase from n equal to 4 to n equal to 8 is very marginal. And for computational reasons, we fix n equal to 4 as the array limit for our analysis. And let me break this plot down a bit for you. Let me fix the baseline, the separation between the two elements, as lambda max by 2. So lambda max is wavelength corresponding to 40 megahertz, lambda min is wavelength corresponding to 200 megahertz. And if you see the ratio of B by lambda, when I fix B as lambda max by 2, I probe a region here. So when it is lambda max by 2, it's 0.5. When it's lambda min, it's 2.5. So essentially your interferometer is probing this region in this U plane, and the radiometer probes the 0 baseline. So you can fix the baseline and solve the response in terms of wavelength, and that is shown over here. So that integral solved for a function of wavelength is this plot, which is essentially this region in the UV plot. So that it is very apparent here, n equal to 4 and n equal to 8, the increase is marginal. So that's why if you fix the n equal to 4 as our array configuration. And the one more thing to note here is that in terms of wavelength, or it can be plotted in frequency as well, there are null responses, which means your interferometer is blind at those frequencies or wavelengths. And this is an issue because we want uniform sampling of your frequency space, and for that you build multiple baselines of different lengths. So this plot here shows a fixed baseline separation, 3 different baseline separations starting from lambda max all the way to 2.5 lambda max, and these are the responses in frequency axis. So you can see that if there is a null response for a particular baseline at a particular frequency, at that frequency you would get a finite response from the other baselines. And eventually when you combine the baseline data, you would sample your frequency space fully and there won't be any null responses. And so to increase the response, you are taking an array of interferometer elements. To sample your frequency space, you need multiple baselines of different lengths. And that's the result of these two arguments. You have n equal to 4 array, there are 4 rows, and you have 6 baselines. So essentially the shortest baseline can be the physical separation, but here we have taken the mutual crosstalk, which is of the order of d square by lambda for the antennas, to be the shortest distance you can go for the baseline, which is lambda by 4 for this, actually lambda max by 4. And essentially you have 6 baselines starting from the very shortest baseline possible. And for a lack of a better name, let's just call it 6 baselines n equal to 4 array. And so you can plot the responses for all these 6 individual baselines in frequency. And as you can see in the frequency space, you have sampled the frequency points very well. You have 6 responses. Now you can combine these responses by weighting your baselines as per your science goals. One of the way is to weight inverse noise weighting, where you weight each baselines by inverse of the noise. So here the SNR plot shown there is actually comparing the interferometer's SNR for your signal, which is monopole, and the noise term is essentially radiometer noise, determined by the term in the last over there, which is under TB is the brightness temperature of your foregrounds. At these frequencies, it's like a power law, so it's an average response over there, and you find your SNR of your monopole signal with respect to the thermal noise. And this is the plot we get for 40 to 200 megahertz. It goes from 15 dBs to 30 dBs. I'll get back to this in terms of, in a later point of this talk. Now the interferometer sees not only the signal, it also sees the foregrounds as well. And you need to fold in the effects of foregrounds as well. And for this, we use BiGSM. From 40 to 200 megahertz, you simulate the diffuse emissions of the foregrounds, and you fold in this with the integral. So remember the integral, visibility integral that I talked about? The E sky we had substituted a monopole sky. Now you need to put in the values of a foreground's temperature itself. So that integral is in theta and phi. So every time your integral queries a particular theta phi, you need to locate the pixel that is located along that direction, get the brightness temperature of that pixel, and input it into the integral. And if you solve that, you can get the response for what your interferometer sees for the foregrounds. And these are some of the demonstrative plots. So this map is at 40 megahertz. This is what your full sky looks like for foregrounds. You have point sources to extend emissions like North Polar Spur, and there are angular fluctuations in all the scales. And if you solve that integral for this sky, these are the real and the imaginary parts. So real part is again going down like a sinc function, and the imaginary part, curiously this time, is non-zero. So essentially the same argument applies here. Imaginary part capture the phase of the sky distribution, and since you have so many angular features here, your imaginary part is non-zero. It was 0 for the case of a monopole sky. And essentially you need to take the absolute magnitude of these two. Before we were just taking the real part because imaginary was 0. And for a typical sine square beam, and for the same 6 baseline n equal to 4 array, you can get the responses in frequency for foregrounds. Something like this. This is just beam normalized. You can see high power values for the foregrounds, and this is the real part, and that is the imaginary part. So you can repeat this experiment, repeat this task for the Gaussian narrow beam as well. So the sine square beams are very broad. Just to show a contrast, the narrow beam Gaussian beams are about 5 degrees, and essentially you do the same exercise with the narrow beam. It turns out that the complex part of the integral is having a higher value compared to the sine square, and this checks out because your Gaussian beam being narrow is able to probe finer scales and resolve out the features in the foregrounds, and essentially it would have higher amplitude in phase. So you can normalize these plots for zero baseline normalization to get a band pass. And that plot is this. So for this interferometer, if it's looking at foregrounds, this is what your band pass in frequency looks like after normalizing the previous plot. And essentially the same, you do the same task of combining the data from all the 6 baselines and you generate your SNR plots. And let me break this plot down a bit. So we'll focus on firstly on what a radiometer, single element radiometer sees. So for a signal or a monopole sky, this cyan plot over there is your SNR for a radiometer case. And the orange plot over on the top is what your radiometer sees for the foregrounds. So you can see that the dynamic range between foregrounds and signal is about 50 dB, and that checks out also in real units. Your signals are of millikelvins and your foregrounds are of 100 or thousands of kelvins. So that dynamic range is being shown in the log scale here. Now the blue plot over here is what your interferometer sees for just a monopole sky. And as expected, it's lower in SNR compared to the radiometer case of SAN plot over here. And the yellow and the black plot over there are for the sine and the Gaussian beams of the interferometer for response for a foreground sky. So essentially, there is a curious thing that pops up here. The reduction in foreground powers when interferometer is seeing. So as you can see here, there is about 10 dB reduction in the foreground power, but there is not much reduction in the signal powers. So effectively, this is very tentative results, take it with a pinch of salt. The dynamic range between your foregrounds and signal has reduced by 10 dB in the case of the interferometers. And this can be a bonus if true, and this requires further analysis to check it out. So I would like to point out that the previous result is very naive stage, and this is just an added bonus because remember the original motivation was that additive systematics are removed in interferometers, and if at all this is true, this is a very added big bonus. And this is a summary slide. I would mention whatever I said right now, and just to add that we are in the SK era, and SK has a lot of short baselines, and the prospects of interferometers look good, and SK can be a test bed for this work. Thanks a lot.
Just go to the slide where you telescope response function, the real and imaginary part, the value are very different. This for real and imaginary.
As the monopole sky had 0 response in imaginary, this has a non-zero response. So this is just phase, and this is the magnitude. So phase components are generally for smaller amplitudes.
Next.
So I saw your foreground that you will observe with interferometer. So it changes the spectral nature of the foregrounds, right? The interferometer observation. So will that create any problem?
This actually depends on your baselines, because given baseline would be sensitive to given spatial mode, and that would show up in frequency like those features.
For example, one dip can look like the signal, right? For example, the radius signal, this kind of use dip can be called by foreground, so will that?
Yes, indeed. And I think that is being shown in this also, but not as drastically as can be seen here. So it depends on your geometry of the array itself.
Any other questions?
Maybe many baselines will have, right?
Yes, SK will, to be precise, antennas in that station.
Any other questions? If no, thanks.